All right, so yesterday we talked about our rational zero. We had the rational zero theorem, so we're going to look at some irrational zeros today. You have two sets of notes. We're not doing all of the examples on both of them. I don't think it's necessary. So we are going to start with irrational zeros. This is going on page 56 when we're done. Okay. And so remember, our rational zeros means that they can be written in the form of a what? Fraction. Okay, so they don't have to be a fraction. If I give you the decimal 0.75, that's a rational number because we could represent it as 3/4, right? So irrational would be like pi is an irrational number, square roots are irrational numbers. They're still real numbers. You just cannot represent them with a fraction. So let's look at this. It says find all zeros, write answers in simplest form. So on number 1, we have a 4th degree polynomial, but it's set up in such a way that we can treat it as a quadratic to try and at least factor it. So let's see if we can factor it. If we can factor it, then this would be x squared and x squared here. This is positive, so the signs are the same. They would both have to be negative. And what do we get here? -6 and -3. Or -3 and -6. It doesn't matter, right? But when you get it can I factor this anymore right now? No, I cannot factor it anymore. So if I'm going to say that this is my fully factored form, then I can't just leave it like this, which many of you have done and I've taken off for on your quizzes and on your tests, and I will continue to do that. That's just technically an expression or an incomplete equation. That is equal to f of x. If you do not finish that off, then I don't know what it's equal to. Is that g of x? Is it equal to 5? I don't know because you didn't say. Okay, so then I need to solve it. Sorry, I'm trying not to sneeze. Okay, so even though I can't factor it anymore, I can still take these two factors that I have and set them equal to 0. So x squared minus 6 equals 0, which means that x squared equals 6. What does x equal? What's x equal? I'm going to kick every single, thank you. I was about to kick everybody out of here. Thank you. Plus or minus? Plus or minus the square root of 6. Y'all know that. I know you know that. Stop making that mistake. Okay, so then I also know that x squared minus 3 equals 0. So x squared equals 3, which means x equals what? Plus or minus the square root of 3, right? Super simple. Don't mess it up. So I have 4 real zeros here. And they are plus or minus the square root of 6 and plus or minus the square root of 3. Okay, everybody good with that? Easy enough? Now, if I had factored this, and, well, let's just do number 2 and then we'll talk about that. All right, so let's look at number 2. I want you to go ahead and get that one factored. If you need more room because you need to do your grouping or whatever, you can use this blank space over here. But I'll give you a second to get that started factoring. So those are your first terms, 4x squared and x squared. And so what goes with the 4x squared? This would be 4x squared what? Minus 1, and x squared minus 8. Okay. And however you got there, if you did grouping, if you did divide and slide, whatever makes the most sense to you, but just make sure that it's an actual process. Now, if I stopped here and solved it, I would still get the same correct answers if I did it correctly. However, is it completely factored? No, it is not. And so when you're supposed to have things completely factored, regardless of whether or not you get the right zeros, if it's not factored, it's not factored. Sometimes that doesn't matter, and all you need is zeros. It doesn't matter either way. But make sure you know how to completely factor it, because I can factor this some more, because this is called a what? Well, you're on the right track. Difference of squares. Okay, but because they are both perfect squares. So this would give me 2x plus 1 and 2x minus 1. And then that x squared minus 8, I cannot factor anymore. And that is my fully factored one right there. Okay? All right, so then I solve them, right? So I've got 2x plus 1 equals 0, which means x equals what? Negative 1/2. And then 2x minus 1 equals 0, so x equals 1/2. And then x squared minus 8 equals 0. So x squared equals 8. What does x equal? Plus or minus? Close. It's my final answer. Is it the square root of 8? Good. So this does give me x equals plus or minus the square root of 8, but then I can simplify that and it's 2 square root of 2. So remember that remind that I sent you? Oh, I shouldn't have boxed that. It's not really my final answer. But that remind I sent you yesterday. You got to be able to simplify your square roots, do quadratic formula, factor, all that good kind of stuff. So in the end, my zeros then are plus or minus 1/2 and plus or minus 2 square root of 2. We're good? Any questions? All right. I know you know those things. You got to make sure you're not making those silly little mistakes. We're going to skip number 3. Let's go ahead and go to number 4. And I want you to factor that one. So I get to there. Can I factor it anymore? No. Okay. This is not a difference of squares here, and that obviously can't be factored. So that is my fully factored form. So then I know over here x equals 5, right? And over here 3x squared minus 4 equals 0. So 3x squared equals 4. X squared equals 4/3. So x equals plus or minus square root of 4/3. Can I leave it like that? No. So this can become plus or minus. So I can take the square root of 4. That gives me 2 over the square root of 3. Can I leave it like that? No. So what does this become? Plus or minus 2 square root of 3 over 3. Good job. Okay, we should be able to rationalize our denominators, simplify our square roots. Those things, especially when the numbers are semi-nice, that should not be anything that's hanging you up at any point anymore. So my zeros then are plus or minus 2 square root of 3 over 3 and 5. Now, so I want you to notice something here. On the very first one I did, even here, I wrote all these little things out, which I know you don't all need to do anymore. Here I didn't, with just x equals 5. And I know you may not need to write out as much on some of the other ones. However, I saw way too many times on the test, and you may not make the mistake here so much, but like this, if this was 2x plus 3, and so that would give me like negative 3/2, I would have seen a lot of negative 2/3. Because you're not really thinking about it that much, because you are flying through it because it's simple and you're getting those numbers backwards. I know you know how to do it correctly. You know how to do it correctly. Sometimes it's worth it to at least write one more thing down so you don't, subtract the wrong one and divide the wrong way because you're just not paying attention to the details. Because you can do it, but if you get them upside down, it makes it wrong. So, any questions on any of these? All right, awesome. So then we look at number 5. So number 5, we're going to pretend like it doesn't factor. Okay, because it wasn't supposed to, and it does, so we wouldn't have to do it the way we're going to do it, but we're going to pretend like it doesn't. So we're going to use the rational zero theorem, even though we have some irrational numbers here. So we're going to start basically by doing what we were doing yesterday. We're combining the things here. So we're going to list all the possible rational zeros, so all of my possible ones. When the leading coefficient is 1, that's really nice, because my possible ones are just the factors of the constant term. So I can start with plus or minus 1. 2 works in there. Can I use 3? Yes. Can I use 4? Can I use 5? Nope. Can I use 6? Yes, okay, so 6 squared is 36, which means I'm halfway, so now I don't have to think through every other number. I know I just have to figure out, well, 4 times that would be 9, 3 times 12, 2 times what? 18, and then 1 times 36. So there are my possibilities. Okay. So I'll start with 1. And I'm going to have 1, negative 2, negative 18, and 36. So go ahead and work through that without me talking you through it, because you don't need me to. So 1, sadly, doesn't work, right? So we would move on to negative 1, because we don't know any other thing to do right now. Move on to negative 1. So 1, negative 2, 18, 36. That one don't work either, right? So 1 and negative 1 are out. So then I can go with 2. See what happens here. So 1, negative 2, negative 18, 36. 1, 2, 0, 0. Oh, finally, right? So we got one that works. That means that I know that f of x equals, since my 0 is 2, my binomial would be what? X minus 2. And then that leaves me with what down here? X squared minus 18. Can I factor this anymore? No. Okay, can't factor it anymore because this is not a difference of 2 squares, right? So I need to solve it at this point. Here I know that x equals 2. Here I would get that x squared equals 18. So x equals what? Plus or minus? Good. 3 square root of 2. And if you need to write down square root of 18 and think through it that way or whatever, that's fine. But hopefully these are getting a little bit easier for you to process. So your zeros in the end then are 2 and plus or minus 3 square root of 2. Okay. But wait, there's more? What more is there? What do you mean the order? Oh, well, well, it just depends. Because 3 squared root of 2 is actually bigger than 2, but the negative is smaller, so, you know, tomato, tomato, doesn't really matter. The plus or minus, yeah, that's kind of arguable. Yeah, it is a little bit confusing. Alrighty, so flip it over on the back here. Let's look at number 6. All right, so same thing. Now this one, does this one factor? Could I factor this one by grouping? No, this one actually doesn't factor, so which is, I mean, if it factored, we could just factor it, and I know that. So we've got to do our possibilities first. Our leading coefficient is 1, so that's nice. I just need the factors of 15, so plus or minus 1. Do I get to use 2? No, but I can use 3. Can't use 4. Can use 5, which then just leaves me with 15. So I have a whole lot less, right? So since it doesn't factor, my rational zero theorem is what I'm using here then to use synthetic substitution. So I'll start with 1, and it's going to give me 1, negative 5, negative 29, negative 15. So this is 1, 1, negative 4, negative 4, negative 33, 33, and 1 doesn't work. So then I'm going to try negative 1. Both of those are out. So do I move on to 2? No, because 2 is not in my list, right? It's been in most of our lists. It's not in this list. So 2 is a big fat waste of your time. I move on to 3. That's why we have a list, right? So I move on to 3. Make sure you're paying attention to that on your homework, too. Keep going until you find one that works. So when we did the rational zero theorem yesterday, and we were able to come up with a list, we were at an infinite amount. Like, we had no idea what to substitute in. There was an infinite amount of possibilities, right? So that theorem alone narrowed this down from an infinite number of possibilities to 8. So it's a huge difference, right? But would you like to narrow it down even farther so you wouldn't have to go through 4 of them? That's what we're going to do here in just a minute. So we wouldn't necessarily have to go through all of those so many times. It'll help us reduce this part here even more in some cases. In some cases, it's not that helpful. In some cases, it is. But all right, but we're not done with this one. At least I got something that works here. So let's write this out. This gives me f of x equals, thank you, f of x equals, so since this is the 0 that works, this gives me x what? Plus 3, and then that leaves me with x squared minus 8x minus 5. All right, so does this right here factor? Can I factor that? No, because my only factors of 5 are 1 and 5, and I can't make those combined to give me 8, so I can't factor that, which means, what do? You do not give up. That is never the right answer. Do I have to play the song again? Quadratic Formula. There's a reason that song was playing over and over when you came in, right? So here, x equals -3. Done. We're good, right? And then over here, we get x equals -b, which would be a positive 8, plus or minus the square root of b squared, so -8 squared, minus 4 times a, which is 1, times c, which is -5, all over 2a, which is 2 times 1. Get it all substituted in. Quadratic formula is not crazy hard. If you know what it is, you can substitute it in, then it's order of operations. The mistakes that happen are your signs. That's why you got to be very careful when and actually substitute it all in before you start doing weird things or you mess up on the signs. So this gives me 8 plus or minus the square root. -8 squared is 64. -4 times -5 is going to be a positive 20 all over 2. So then that gives me 8 plus or minus the square root of 84 over 2. Can I go ahead and reduce the 8 and the 2? No. What about the 8 and the 84? What about the 2 and the 84? No. Okay. So I need to see, maybe I can't reduce it at all. I need to see if I can simplify this. Well, it's an even number, so is it divisible by 4?
Yes, it is.
Yes, it is. So if it's divisible by 4, what gets to come out? A 2. So I can make this into 8 plus or minus 2 times the square root. All right, what's 84 divided by 4? 21. And just because 4 came out doesn't mean that this is simplified all the way. Keep that in mind. So then I got to double check. Can I take anything else out of the square root? No, because that's just 3 and 7. So at least it would have been simplified partly, even if you could have reduced it again. All right, so can I simplify now? Yes, as long as I can cancel out with all of them. 2 goes into 2 once, and 4 times here. So 4 plus or minus square root of 21. So in the end, my zeros are -3 and 4 plus or minus the square root of 21. Okay. Any questions at all? Same process we've been doing. You're just going to have some irrational numbers. You may be able to just take the square root. You might have to use quadratic formula. Okay, but it should all be old business. Everybody good? So Have you heard the phrase, I think, therefore I am?
No.
Yes. Do you know who said it?
Wait, I think therefore I am.
Okay, good. René Descartes is how you say it. I know it's spelled like Descartes, but it's René Descartes. I think, therefore I am, because he was a French philosopher, mathematician, scientist. We're going to look at his rule of signs here in a minute. I'm going to tell you a little bit more about him, even if you don't care, because somebody's going to care. So French philosopher, mathematician, scientist. Have you heard of the Cartesian coordinate system? No. Do you know what that is?
I'm assuming it's some kind of coordinate.
Very good. It's the stuff you've been using. It's the coordinate plane. It's the X and Y coordinate plane that you've been using forever, okay? It's actually called the Cartesian coordinate system. This is important, and let me tell you why. Years ago, and this has been many, many years now, when we first had some engineering classes, which is way different than the engineering classes we have now, but the engineering teacher came to me one year and said, do y'all not talk about the Cartesian coordinate system at all? And I was like, well, yeah, I mean, that's kind of what Algebra 1's based on. And he's like, well, none of my kids know what it is. I'm like, this is just weird. Well, then I realized that teachers weren't using those words. We talk about the coordinate plane, we talk about the X and Y axis, but that is the Cartesian coordinate system. So you need to know that they're the same thing, so you don't think it's something totally new and totally different, okay? It's named the Cartesian coordinate system because René Descartes is the one that created it, or, you know, semi-discovered it, I guess, discovered that it worked. But he's the one that first connected geometry and algebra so that you could look at things on the coordinate plane and solve for things. He's the first one to use X, Y, and Z to represent variables, and A, B, and C to represent constants to kind of make that separation. And the first one to use the superscripts as the exponents. So he's kind of created most of the system that we use for math to make it make sense and make sense no matter what language you speak or whatever, what country you're in. He used the law of refraction to determine that a rainbow's angular radius is 42 degrees. So if you ever wondered, like rainbows always kind of look the same, right? Their angular radius is 42 degrees. Using the law of refraction, that's how he figured it out. So he used the law of refraction, but he actually developed the law of reflection. So you'll probably talk about him in your science classes too, if you haven't already, and you know, maybe in your history classes as far as the philosophy part of that goes. But one of the many things he is responsible for is the rule of signs. That's why it's called the Descartes rule of signs, and this goes on page 57. And there should be a little apostrophe here because his last name actually has an S in it. So the Descartes rule of signs. So in many cases, the following rule, discovered by French philosopher and mathematician René Descartes in 1637, is helpful in eliminating possible zeros. This is nice. We want to eliminate possible zeros from a lengthy list. So to understand this rule, first we must look at the variation in signs in a polynomial function. When a polynomial function is written in standard form, kind of like this right here, a variation in sign occurs when consecutive coefficients have opposite signs. Okay, so when consecutive coefficients have opposite signs. His rule is actually very, very easy to use. Okay, it's not a complicated thing at all, and it can help simplify what you're doing. So it says, how many variation in signs does this function below have? So if I just look at this one, here's what's happening. This coefficient is positive. Then this one's negative. So that's a change right there. That's your first change. This is negative. This is positive. That's change number 2. Then it's still positive. Then positive changes to negative. That's the third one. And then it stays negative. So there are 3 variations in signs. That's how easy it is to come up with the numbers that we need to come up with, right? EJ. All right, we good? Now, Descartes' rule of signs, here's what the rule actually says after you can figure out how to find the variations. Given the polynomial written in standard form with real coefficients, so we don't have any imaginary stuff yet, the number of positive real zeros is equal to the number of variations in f of x, or less than that by an even number. Okay, and I'll explain a little bit more what that means. And then the negative real zeros is equal to the number of variations in the signs of f of negative x, or less than that by an even number. Okay, so the Descartes rule of signs includes the repeated zeros. So a 0 with multiplicity of m counts as m zeros. So if I have, x minus 2 squared, then the 2 is a 0 and it counts as 2 because it's what's called a double root. All right, so here's what we're looking for here. It says state the possible number of positive, negative. That's all we're looking for. We're not looking for the zeros themselves, just how many possible positive and negative we have. So if I look here at this one, we start with the negative, right? It changes to positive, stays positive, then changes to negative, then changes to positive again, right? So that means my possibles for my positive, I have 3, right, because there's 3 variations, or less than that by an even number, so 3 or what? Less by an even number, like not less by 1, but it'd be less by 2, yeah, 1. Okay. So 3, or I can subtract an even number and get 1. So basically you want to subtract by 2s because we're not going to get any ginormous numbers here. So then to figure out my possible negatives, I have to find f of negative x. F of negative x is super easy, so do not make it harder than it is. When I substitute in a negative x, if I have an even exponent, what happens? It's positive, right? If I have an odd exponent, it's negative, right? So if it's an even exponent, the sign stays the same. If it's an odd exponent, the sign changes. That's all that's happening here. So even exponent, my sign stays the same. Odd exponent, my sign changes. Even stays the same. Odd, the sign changes, and then your constant would never change. So then we look for the variation in signs here. This is negative, negative, changes to positive, stays negative. So your possible number of negative real zeros would be 1. I can't go less than that by an even number because that would give me a negative number of real zeros, and that doesn't make any sense. Okay, so positive, 3 or 1, negative. Now, how's this going to help me? Well, when we're going and using the rational zero theorem, if I go through and I figure out that negative 1 is a 0, and I still can't factor, so I got to go back and do some more. Well, if I know that there's only there is exactly one possible negative, and once I get it, am I going to try any other negative numbers? No, that's a complete waste of my time. I've just cut my list in half, basically, because the negatives don't mean anything to me anymore. Does that make sense to you? Okay, so look at number 2. How many variations we go? 1, 2, 3, 4, right? So positive then, I could have 4, 2, or 0. Maybe there's not any positive ones. Okay, that's possible. I could have all negative ones. Then I need to find f of negative x. So that's going to give me, this is an odd exponent, so it changes to negative x to the 5th. Even exponent stays the same. Odd changes the sign. Even stays the same. Odd changes the sign. And then the constant is always just the constant. Okay, do you all agree with 1? Yes, because this is all negative, changes to positive, and then no other change happens. So exactly 1, negative 1. So if you had to decide, in this case, whether to start with 1 or negative 1, I would start with the negatives until I find my negative 1, because I might not have any positive ones. Might be 0, might be 4, but it just depends. All right, so you do number 3. All right, how many positives? 0. There's no variation, right? So I chopped my list in half before I ever even started. I don't even have to try any of the positive ones. Then how many negatives? Be 2 or 0. So I could have none. They could all be imaginary, right? Maybe it doesn't touch the x-axis at all. That's a possibility, right? Okay, we all good with that? Any questions? All right, do number 4. How many positives? 1, exactly 1, right? How many negatives? 0. Okay, we good? Easy enough? All right, so let's see how that can actually help us here. Let's flip over on the back. All right, so we're going to create a list of all the possible rational zeros, find all the real zeros, and use Descartes' rule of signs to help us eliminate the possibilities. So we got to start off just like we're going to use the rational zero theorem, which means I got to find my total possibilities. So my possible zeros would just be the factors of 8, so plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Everybody agree with that? So in order to figure out my number of possible positive and negative, I'm also going to need f of negative x. So I'm just going to go ahead and find that. This is going to give me x to the 4th minus 6x cubed plus 7x squared plus 6x minus 8. Okay, so how many possible positives do I have? 1. Okay, so that means there's exactly 1, because 0 is not an option. So there is exactly 1 positive real solution. What about negative? 1, 2, 3, or 1. It could be 3 or 1. It's not a guarantee that it's 3. All right, so knowing that, I don't have any zeros, so it doesn't chop my list in half right this second or anything. But go ahead and start with, I'd start with find my positive one, since I know that there's exactly 1 of them. So we'll start with 1. I'm going to use that and get 1, 6, and make sure when you're doing that you're actually using f of x and not the f of negative x you wrote down. And then negative 6 and negative 8. Oh, that's not negative. Hang on a second, I'm writing down the wrong thing. All right, so isn't it just a glorious day when the first one works? All right, so positive 1 works. So what does that tell me now? That there are no more positives. So there's only 1. I just found it, right? That's it. So all the rest of my positive numbers, not even an option. Okay, so let me write down, let me see if I even need to go any farther with that anyway. So that would mean that f of x is equal to, well, if that's 1, that's going to be x minus 1. So it's x to the 4th, so this is x cubed plus 7x squared plus 14x plus 8. Okay, so can I factor that? Well, maybe you can, but I can't. Okay, so no, it doesn't factor. So I know that positive ones are out the window. I would most likely go to negative 1 next anyway. But so let's go to negative 1, and then I'm going to use my reduced ones. So 1, 7, 14, and 8. It's just another glorious outcome, isn't it? So we get x minus 1 times x plus 1 times x squared plus 6x plus 8. So it's possible that I'm only going to have 1 positive and 1 negative, right? Maybe I don't get any real solutions from this, or maybe I do. Can I factor this? Yes, this does factor, so I don't need to go back to that at all. So this is going to give me f of x equals x minus 1 times x plus 1, and then x plus 2, x plus 4. So now I have it fully factored, can find my zeros. So this right here gives me the plus or minus, and then -2 and -4, which again, those are, well, probably should have put -4 first, but it's fine. Plus or minus, we can put all together. So I have this, and this is my answer. Now, let's look back at what we did. Did Descartes' rule of signs really help me on this one? No, because most likely I would have gone with 1 and then -1 anyway, but it's not always going to happen. We ended up with like a -3 on another one, right? We had to go through a bunch of them. So this probably wasn't the best example to see how it could help you, but at least you know that if you had to go farther, that you would not use any more of the positive ones, okay? Use it to your benefit. And then look at what you have. You have 1 positive and 1, 2, 3 negative real zeros, okay? We good? So you can check yourself, because if you only have 2, if you have 2 negatives, that's bad because 2 is not even an option, okay? Any questions? All right, we are not going to do the next one, so we're done. You can go ahead and fold those, put them in your, glue them in your ISN now while you have time. These assignments shouldn't be difficult, they're just kind of tedious, but you can do it so the process makes sense for when we keep adding pieces to it.